be Professor Taguchi, who will speak of congruence of Galois representations of function fields.
Okay, thank you very much for the introduction, and I'd like to thank the organizers, especially Sugil-so, for invitation. And I'm very happy to come back to this beautiful campus of Yonsei University. The title on congruences of Galois representations of function fields is the title for the third lecture, and in the first two lectures I will give very basic stuff on function field arithmetic. But let me begin with an introduction to the third third lecture. So to give some motivation, and let K be a global field. So a finite extension of Q, or the rational function field in one variable over a finite field, and let V be a place, a finite place. Okay, and let T and T prime be two ZL modules with continuous Galois action. So here let me be a bit vague. So this is I always denote by G sub K the absolute Galois group of K. So K bar is the separable closure of K, and L is prime number. And so I want a theorem of the type, this type of theorem. So suppose T and T prime are congruent mod L. So this means that T divided by LT and T prime divided by T prime are isomorphic as GV representation. So the GV is the decomposition group at V. So this is in GK. And then I ask if these are isomorphic as GV representation. So this is a FL linear representation, and this is a ZL linear representation. And so this is the question. And of course, this is absurd in general, impossible in general. So, for example, there are many liftings of T mod L, and they are governed by the so-called deformation theory. So there are many, and so I impose here a condition. So either global, some global condition, or some conditions at other places. then maybe this kind of statement can hold. Since this is a little bit abstract, I would like to explain some motivations for this. And here I put ZL to be familiar with you. But in the third lecture, here I consider kind of characteristic P analog. So because so I'm considering our representations arising from kind of Dirichlet modules, etc. And so a similar theorem can be proved for ZL coefficients, but I chose to work in the function field case this time because, for one thing, there are many people, speakers are presenting the characteristic zero case, and I think I was afraid that I would have nothing to add to their talks. And another reason is that function field arithmetic is less popular, so I wanted to try to popularize. And anyway, so the motivation was, but however, in the number field case. So, so my plan is as follows. So the first I give introduction and motivation. And the first section is the function field arithmetic, especially Dirichlet modules. And second, I would like to explain a kind of higher dimensional generalization of Dirichlet modules. So this is T motives. And the third section is the congruences. So there are 4 sections, and I have 3 times. So each time I give 4 thirds, and so my plan is like this, and division is always difficult. So I'm not very sure about my timing. Anyway, so let me explain the motivation. So motivation. So this is a conjecture of Rasmussen and Tamagawa. So this is published in 2008. So suppose we are given a number field and an integer g, then the conjecture is that there exists a constant depending on k and g, such that for any prime number L larger than C, there exists no abelian variety A over K of dimension equal to G. Such that, for one thing, A has good reduction outside L, and so let me denote by this the set of L torsion points over the separable closure K set K bar of A. So this the semi-simplification of this Galois module is isomorphic to some power, the sum of some powers of cyclotomic characters. So this chi bar is the mod L cyclotomic character. So, so in the matrix form, it is like this. So this is the conjecture of Rasmussen and Tamagawa. As Falting proved, and which was a conjecture of Shafarevich, that there are only finitely many abelian varieties over a fixed number field which have good reduction at L, outside L, and but this conjecture says that if we move the bad place L, and if we pose some condition on L, AL, there are only finitely many such pairs of A and L. And here we have a congruence condition. So this means that the Tate module is congruent to a special type of Galois representation, mod L, up to semi-simplification. And so this is known only a few cases. So known if in a few special cases. So in Rasmussen and Tamagawa's paper, like elliptic curves over Q and elliptic curves over quadratic fields, and a few cases, and also it is known by them in general under generalized Riemann hypothesis. This is not published. This is not in their paper, but they claim that they prove this. And also, in case A is semi-stable, for the moment, I mean A has everywhere semi-stable reduction, but actually we only need to A to have semi-stable reduction at two special places, and Also, in case Galois image on TLA at the Tate module is abelian. So these are due to Ozeki. So I tried to consider the T-motive case. So before going to function field case, maybe it is interesting to explain their motivation for this conjecture. So Rasmussen Tamagawa's motivation, because this is somewhere in another topic, and maybe this is actually Rasmussen's motivation, as I hear from Tamagawa. But anyway, this is explained in their paper, joint paper, and their motivation is in Anderson-Ihara theory. Anderson-Ihara's problem. So this is another interesting topic. So here, let M of L be the maximal Proel extension of Q of mu L. So this is the group of roots of earth roots of unity, unramified outside L, and let Q of L be the field which could be written pi 1 pro L of P1 P1 Q bar minus 0 1 infinity. So this is so this is the field of definition of all Proel coverings of P1 minus these 3 points of L power order. But this can be realized, written very explicitly as the field obtained by adjoining all higher circular units, circular L units. So these are L power roots of cyclotomic units, and they are one minus of these elements, and anyway, so they are made of cyclotomic elements inductively, and it can be shown that this is a subfield of ML. So the problem was problem of Anderson-Ihara is so if these fields coincide or not, and so Rasmussen's approach is to use Rasmussen's approach. I'm sorry to abbreviate as R. So here I wrote some conditions on A. So A is good reduction outside L, and A of L is some blah blah blah. So let me denote by this condition by star. Then if A is as in star, then then sorry, this A is over Q. Then the field generated by L power torsion points so this is contained in ML, because by the theorem of Searle-Tate, this is unramified outside L, and if the representation is if it is like the mod L representation is like this, then the Galois image is pro L over this Lth cyclotomic field. So this is contained in ML, and so if ML is equal to QL, we should be this field should be contained in QL. So this is as in direct evidence. And this is actually known for in a few cases. For example, if A is the Jacobian of a Fermat curve of L power degree, then by Anderson-Ihara, it is a subfield of this. And in some for elliptic curves and L2 or 3, Rasmussen also proved this. And for some modular curves, Rasmussen and Papa Nicholas proved this. So this is so he wanted to prove this for all abelian varieties, but how many such pair of A and L. So this is a kind of indirect motivation for theirs.
Problem is known for, I mean, as long as Francis Brown's work, where he proved the Leigh-Ihara conjecture held up, then this problem is known for all regular primes.
Yeah. Oh, really?
Yeah, that's I had proven in a paper once that if the Leigh-Ihara conjecture is true, then this holds for all.
Oh, really? Yeah. Sorry. Yeah, thank you very much. Yes. Okay. So, okay, now let's go to the function field. The analogy between algebraic number field and function field have long been known, and recently there is a third party, the three-dimensional hyperbolic manifolds, or for example, three-dimensional sphere minus knots. And these are said to be analogous. So this should be also analogous. And this part has nothing to do with today's talk. For this, maybe you can consult Morishita's book. And and as you know, Iwasawa imported many ideas from function fields into number theory to form Iwasawa theory. And Drinfeld, on the other hand, constructed some function field analog of, for example, elliptic curves. And the interesting thing is that the composition is not the identity. And so let me recall some of these analogs. So these are well known, and so this is the value place defined by 1 over t, and we have these analogs. And what is the analog of an elliptic curve? Well, we have elliptic curves over function fields, but they are not what we want now. Or even abelian varieties, or the multiplicative group. What are the analogs of these things? So correct way to think about these is that so to consider the endomorphism ring of an elliptic curve. Then at least there is always this contains a ring isomorphic to Z, and sometimes this contains an order of quadratic, imaginary quadratic field. Imaginary quadratic field, and so following those analogies, we want to put, for example, polynomial ring here. So I will denote this by A and this by F. And I will never use abelian variety from now on. So so we want to have something like this. And so if K is a field of characteristic 0, then we have a nice object here, end of the additive group. So technically, this is a functor from K algebras to abelian groups, which associate. So R is an K algebra, and this is an additive group of R. So maybe you can just think of this as a K bar or something. And if this K has characteristic 0, this is just K, just multiplication by K. But in characteristic P, we have Frobenius here. So this is actually tau. Let me write P here. Here tau P is the Frobenius. So raising x to the pth power. So this is a non-commutative ring, and its commutation relation is or if we think of this as a polynomial ring, this is just sorry. Sorry?
What is K in this example?
K.
K is F. P.
This K? This K is any field of characteristic P. Yeah, sorry, I'm sorry. But if we think of this as a polynomial map, we could write this as x to the pi. So in some sense, this is a subset of regular functions on A1. Yeah, and later I often consider on only FQ linear. So now I suppose K contains FQ, a finite extension of FP. So this is a twisted polynomial ring over tau. Let me write tau for the qth power map. And so according to various references, people write this also phi or sigma, and yeah, the notation tau is due to Anderson. And, okay, so now I would like to give the definition of Dirichlet modules, and but before that I have to fix a structure of K. So an A field K is a field given ring homomorphism from A to K, and the kernel of this map is denoted characteristic of K. So this prime ideal plays the same role as the usual characteristic of a field in the function field setting. And Dirichlet modules. So Dirichlet A module of an A field K of rank R is ring homomorphism phi from A to end K GA such that the image of A is polynomial in tau, and yeah. Such that the first term is the image of A by this structure morphism, and AN, the top term, is not 0, and this N is R times degree of A. So this is the rank of the Dirichlet module. So since this is a ring homomorphism, and now A is the polynomial ring, this phi is determined by the image of T, one element T. But in general, we can define Dirichlet A modules for more general type of A. Can define so if we can define Dirichlet A module for any kind of finite extension of FQT. But let me concentrate on the polynomial ring case this time. And yeah. And the morphism of Dirichlet modules. So this is a morphism of underlying GA. So F is in fact an element of GA such that which is compatible with the action given by phi 1 and phi 2. So a typical example of Dirichlet modules is yeah, so this is called Carlit module. Carlit is a person of very old generation, and he studied this kind of thing in the early 20th century, and so he's much before Dirichlet. Yeah. So, but he studied this very special case. So, so it is often denoted by C. And the action of T is given by theta plus tau. Here, theta is the image of T. So here, the image of T is always denoted by theta. So in terms of polynomial, Ct of x is theta times x time plus x to the qth. And had been noticed that this Carlit module gives rise to an analog of cyclotomic theory. So in cyclotomic theory, we use the multiplicative group. The division. We use division points of the multiplicative group. So this is just the roots of unity. And in Carlit's theory, we use division points of Carlit's module. So, for example, the roots of this polynomial, so they are 0 and q minus first root of minus theta. So this is just a Kumma extension, but this is this generates the analog of teeth cyclotomic extension, Carlit cyclotomic extension. So this kind of analog. This is the simplest non-trivial dream field module, and it has rank 1. And for dream field module also, it would be nice to have an analog of so an elliptic curve can be over C can be written as a C modulo lattice. So and in dream field module, for dream field modules also we have yeah. So let C infinity be the here we can take the completion, but we don't need to. So we can do both, but maybe I like to. I prefer to put hat and lattice. Lattice. Maybe a lattice in C infinity is free of rank R, free A module of rank R, which is discrete with respect to the topology of C. In the case of classical complex number field, we have only discrete submodules of rank 1 and 2, and dividing by rank 1 submodule, we get a multiplicative group, and dividing by rank 2 lattice, we get a elliptic curve. But in this field, we have lattice of arbitrary rank R. And a theorem due to dream field is that there is a categorical equivalence of dream field. Let me simply write dm of a dream field module of rank R, and the A lattice of rank R in C. This is over C infinity. In C infinity. Modulo isomorphism, and here isomorphism of lattice is homothety. So lattice and its constant multiple is said to be equivalent. And this correspondence can be best described by the following diagram. So so the quotient of this C infinity by the lattice is again isomorphic to additive group of C infinity. And so here we have usual multiplication by an element of A. And since this is an A lattice here, and here the action of A is given by pi A. So for any lattice, we can find a Dirichlet module which sits in this place. And conversely, if we are given a Dirichlet module, then we can define a exponential function, kind of exponential function, and whose kernel is a discrete submodule, and it gives the lattice. If a lambda is given, this function can be defined to be this. So it looks like a sine function, but it plays the role of exponential function. Yeah, this way. So this is analogous to, so in the classical case, we have, in place of this, we have Weierstrass P function. Yeah. So this equivalence gives an idea about how many Dirichlet modules are there for each rank R, and because the basis of this kind of lattice has R elements, but we have this kind of identification. So the dimension should be R minus 1. So how many Dirichlet modules are there? So very vaguely put, we can construct the moduli scheme of Dirichlet modules. So over the field C infinity, the moduli can be constructed by the quotient of C infinity by kind of SL to A. So in fact, we can define a Dirichlet module over any A algebra, A scheme, and the moduli scheme is of relative dimension R minus 1. And if we put a suitable level structure, then it is smooth. Smooth over A, and it is smooth outside the level. But we don't go into the detail now. Yeah. And since I will be talking about Galois representations, so let me explain the Tate module. So if phi is a Dirichlet module over a field of K, and V is a prime of A, and different from characteristic of K in the former sense, then let's define us. So now for any A, define phi of A to be the kernel of phi A of GA K set to GA. So if you think of this as a polynomial, this is just the roots of that polynomial, and this is actually isomorphic to A over A to the R. So if this is of rank R, and to define the Tate module, you just take the limit and here the absolute Galois group acts continuously, and this is isomorphic to AV to the R. And for example, it is known that so if K, so this F is the fraction field of A, and is finite. So this is the analog of usual algebraic number field. Then B, so this is semi-simple as FB GK module, and second, so this is the analog of Tate conjecture. So so this is isomorphic. Yeah. So this is by myself and independently by Tamagawa. And okay, let me stop here for this.